Hi, welcome to online tutorial videos from JCBRO Labs. For more information and to download the source code of this video, you can visit us at www.jcbrolabs.org. We also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on Matlab, embedded system, Python, machine learning, data science, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org, or you can also mail us at jcbrolabs@gmail.com. So in this video we will talk about how to design filters and how to obtain the frequency response of filters in Python. Okay, so let's start. What to do? Today we are talking about filters. So when we talk about filters, so filters are the devices or electronic circuit or a simple program which is used to filter out the undesired component present in the signal. So undesired is a very related term, so it depends on application to application, right? So there are generally we will be talking about spectral domain filters. That means which will be filtering any signal in the spectral analysis and spectral domain. So basically filters can be divided into two categories, right? First is IIR filters, and which stands for infinite impulse response filters, and another one is the FIR filters, which is finite impulse response filter. So they are named suggest, like in this the impulse response have infinite numbers, while in FIR the impulse response have finite numbers, right? So there are several categories further in IR, like Butterworth filter, Chebyshev filter, or elliptical filter. Similarly, this FIR filter depends on the kind of window which we are using to design the filter, like Kaiser window filter or your elliptical window, Gaussian window, or square window filters. Apart from it, when we talk about the characteristics, based on the characteristics of the filter. So based on the filter characteristics, we can divide filters into some more categories, like low pass, high pass, and band pass. So first category is the LPF, which is known as the low pass filter. So low pass filter means, suppose we are talking about the magnitude spectrum, or you can say the frequency response of the filter. On x-axis we have the frequency, and here we have the magnitude. So its response goes like this. That means up to certain frequencies which are decided by -3 dB bandwidth, which is -3 dB bandwidth. Okay, so if it is 1, you will get 0.707 here, and here this is known as the cutoff frequency FC. So all the frequency component which are present in the signal up to FC, they will be passed, and all the frequency component outside this FC, they will be stopped. So this is known as the pass band, or we can say pass band frequencies, and out away from this it is known as the stop band. So this is the normal frequency response of the low pass filter. Other than that, second category comes is the opposite of this low pass filter, that is the high pass filter. So similar, this low pass high pass could be IIR type or FIR type. Okay, so we will learn how to design this low pass high pass in IIR and FIR in Python. So in HPF it goes like this. That means after certain frequencies, again this is -3 dB bandwidth. So in this case it is pass band, and this is stop band. So again this is FC. So in this case, all the frequency component which are present in the signal above this Fc, right, they will be passed, and frequency component which are below this Fc, they will be stopped. So similarly, we have another category of filters that is known as the band pass filter, or BPF. So as its name suggests, it pass certain band of the frequency. So its frequency response generally goes like this. Okay. Okay, and so it has two minus 3 dB bandwidth. This is 3 dB line. Okay, and this one. So it has two cutoff frequencies, which are known as the lower cutoff and higher cutoff, or we can say FC1 and FC2. Here we have this F. So this portion between these frequencies portion is the pass band, and all the frequency component present here, they will be stopped. So this is stop band. So this filter passed only those frequency component which lies within the pass band range. Okay, and there is another category, or the last category of the filters, which we generally known BSF, or band stop filter, or generally the notch filters. We also say it. So it is just the opposite of the band pass filter. So it goes like this. Okay, so again we have a 3 dB line, minus 3 dB line, and again it has two cutoff frequencies. This is F and this is the magnitude, right? So this range now is the stop band. Okay, so stop band means frequency which will be lying within the range of this FC1 and FC2. All those frequency component will be stopped, and all the frequency which are above this FC2 or which are below this FC1, they will be passed. So these are the pass band. Okay. So these are the four categories of the filters which we generally know: band pass, band stop, and low pass filter, high pass filter, and so on. Now when talking about designing in digital domain, so in digital domain, so remember there is one important thing in digital, that is the sampling frequency. So sampling frequency should be known in order to get the desired response of this filter. Further, this sampling frequency decide what is the cutoff frequencies. Okay, so in digital domain we have normalized frequency. Okay, normalized frequency. So let's say if we have a design requirement like we want a cutoff frequency of a low pass filter as 10 Hertz, right? And we have a sampling frequency of, let's say, 1 kilohertz. So this normalized frequency will be twice of Fc by Fs. Okay, so it is a multiple of pi. This will be a multiple of pi. So from here we will find it. So it will become 2 into 10 divided by 1k, and now it will become in radian per second, right? So we need to define this particular in normalized frequency terms, right? Now we will understand how to convert this frequency into another terms as well. And another important thing which is used that is used as the filter order. Okay, so it decides how fast this filter, or how fast this particular slope, right? So there is a slope of it. So what will be the slope of this depends on the filter order. Okay, so if the slope is high, it will act like a ideal filter. So all the filters characteristics which I have drawn here, those are non-ideal filters, or the practical filter. Ideal filter acts like this. That means sharp cutoff. So it depends on the kind of order of the filter. So if the order is higher, it will follow the ideal filter, but it comes at a certain cost. by the distortion of the filters again. Okay, now we are going to try it in Python. So there is a model or a module in Python which we are going to use. The module is a scipy module is there. So it is a scipy dot signal module in which we can define this low pass, high pass, FIR, IIR filters. Okay, so now let's go to Python programming and let's understand how to design a filter. In order to write a program on Python, we want to make sure we want to mention that we are using Python 3.7 and we are using the spider IDE in order to write the code. Okay, so let's first create it and let's save it. Okay, so let's first import all the modules which will be required for this task. Okay, so let's first create all the open windows so that we don't need to open them again and again. Close all. Okay. So now first we'll design IIR filter or specifically Butterworth filter. Okay. We need to define the sampling frequency. Let's say we are having a sampling frequency of 1000 Hertz. So based on the Nyquist criteria, we can get the response up to 500 Hertz only. Now we will design the filter order. Let's say filter order we are using is 5, and let's say the cutoff frequency of this IIR filter. So cutoff frequency is, let's say we are using 100 Hertz. Okay. So now we will find the normalized frequency. So this is the normalized frequency, and then we will design our filter. Yeah. Okay, so by default it creates the low pass filter, and that's it, and these are the numerator denominator term of the Butterworth filter. So let's try to run it. Okay, it's working fine. Now let's draw the frequency response of the filter. There is a command which gives the frequency response and it returns the frequency values and corresponding magnitude. So there is a command sig.freqz. So it gives us the frequency response of the filter. So in this we need to define the numerator and denominator term, and then we need to define like how much number of samples we want into it. Okay. let's say we want 500 samples, and then we convert this frequency axis again into the hertz form, because this W is in the form of omega. So W divided by, now convert this magnitude in dB form. Okay, now we will plot it. Okay, so let's run it. Yep, so we are getting the passband frequency at 100 Hz. So let's create a grid. Okay, so here we are getting it nearly -3 dB frequency, which is coming at the 100 Hz, exactly the way we have defined it. So okay, we can convert this band low pass filter into high pass filter. Only thing we need to type like filter type equals to high pass. So now this 100 Hz become the high pass cutoff frequency. Yes, this will be the high pass frequency response or filter design. And similarly we can change it to band pass. So in the case of band pass, we need to define two cutoff frequency, right? So we need to make here two cutoff frequency, let's say 100 to 300 Hertz. We want to make the pass band frequencies, and then we need to convert into NP array, because right now it will be a list. So NP dot array. Now this will be fine. Now let's run it. Yep. So this is a high pass band pass filter. Similarly, we can write a band stop filter. Okay. Now let's learn how to design a FIR filter. Okay. In order to design a FIR filter, again we need number of coefficients, because if you have gone through the theory part of a FIR filter, it has only numerator terms. So we have to define number of coefficient. Let's say we want 20 of them, and then we got the tabs, number of tabs required. So command is to generate the FIR filter is sig.fir win, comma 20 number of tabs, comma cutoff frequency. So by default again we are using the same cutoff frequency. Okay, let's define a different one. W underscore C equals to okay, so it will generate a number of tabs. Now get the frequency response of this filter. So W this 2000 is only like number of sample we want in the frequency response, right? So it has nothing to do with the frequency. So in this signal dot frequency we just need to provide this T information, and then we need to convert this W, resultant W, because it is in a radian per second, we need to convert it back into hertz. So for that, Fs into W divided by 2 pi. Okay, fine. Now let's change in h into dB. Now make a plot of it. Make a grid on plt dot grid. Okay. Now let's run it. If everything goes fine, yep, we got the two filters. This is for the first one, FIR, and this is the FIR filter response. Okay, it is very bad. Where we have done something wrong. Yes, because we have plotted h. It is a complex number. We need to plot h underscore db. Yes. So this is the FIR filter. This is 100 Hertz cutoff frequency. So this is also known as the equiripple filter because we got ripples here. So let's change it to 200 and let's see what happens. So obviously its response has shifted to 200. Now try to change it to make it band. Okay. So I hope you understand how to design a filters in Python. More about these filters or the code you can get from the web page or from the documentation of this signal, and how to change several parameters of the filters. So I hope you understand a lot, and if you have any problem or doubt or suggestion, then you can let us know by commenting below this video. Further, we also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on Matlab, machine learning, data science, Python, embedded system, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcprolabs.org, or you can mail us at jcprolabs@gmail.com. So that's it for this video. Thank you.